In this lecture, we're going to talk about 3D mesh generation and CAD pre-processing that goes into constructing of 3D meshes. And so we've talked a little bit about mesh generation on some of these 2D surfaces, but they're more kind of like simple contrived examples that we didn't really have to think a lot about how to construct our mesh. And in practice, mesh generation is a bit of an art, but it also requires you to think about the solution and the problem that you're trying to solve. And so it also is a bit of a puzzle as well. And just as in many things, garbage in means garbage out. Typically, if you've provided your simulation solver a bad mesh, you'll get bad results out as well. And so mesh generation is really something to try to become good at, as it'll enable you to do or to perform really good analyses. So first, what I want to mention is that there are some standard finite element shapes in 3 dimensions, and I've got pretty much like the 4 main ones shown here. That you can have a tetrahedral or a tetrahedron, so that's essentially 4 faces. They're each triangles, or you can have a pyramid, which is a square base or rectangular base, or I suppose a quadrilateral base with then 4 sides that have triangle shapes. There's a triangular prism, sometimes called a wedge element. We also hear it called a pentahedral element. That's essentially an extruded triangle. And so you can see that then it's 2 triangles within 3 faces that are quadrilaterals, and then the hexahedral or hex element. And so of these elements, traditionally the desired standard element to try to construct a mesh out of is the hexahedral element. So they call this hex mesh generation. And there are various reasons for why they're chosen. There's significant mathematical properties that describe how these work. They tend to be robust. They tend to, if you can construct a hexahedral mesh, the problems end up being smaller, typically fewer degrees of freedom. You can align these hexahedral meshes along like surfaces and regions that like stresses that you want to be able to capture accurately are. But what you'll see, and we'll see in this, is that constructing hexahedral meshes is not a trivial problem. And so oftentimes folks will use tetrahedral meshes, as you can typically always construct a tetrahedral mesh of at least okay quality. But there are some challenges with tetrahedral meshes. For instance, in structural mechanics, linear tet meshes will give you the wrong results. Some people will say that they're over stiff, but I prefer just to say that they're wrong, that they're not sufficient for structural mechanics analyses. And so you have to use degree 2 or quadratic tetrahedral elements in structural mechanics problems. And what you just tend to get is you get kind of the problem blows up where you just get a lot of degrees of freedom. So sometimes what you'll do is you'll choose to have hexahedral meshes in areas of problem that you care about, but maybe a tetrahedral mesh in places where you don't really care about. And so you can see how the pyramid element is an element that allows you to kind of transform from the quadrilateral faces of a hexahedral element to the triangular face of a tetrahedral mesh. And then lastly are these triangular prisms. And we may not be able to show it today, but those are most commonly used in cases where you have, say, an extruded cylinder that you're trying to mesh, and you want to have degrees of freedom along the center of the cylinder, and kind of like this radial patterning of elements. And so the innermost rung will be, you can imagine if you have these hexahedral elements, that the inner or the edge that's closest to the radius is going to be a little bit shorter than the edge that's further away from the radius. And at the center, there's going to be essentially a zero length edge, and that's effectively this wedge element. It's typically where they're used. But as I mentioned, typically we're trying to construct these hexahedral meshes. As you can see, they tend to have flow along surfaces and tend to be fairly orthogonal to these surfaces. They just also tend to have, they tend to like just look beautiful. And we'll see that just some of the metrics, or quantitative metrics we use for element quality tend to be things that for whatever reason aesthetically seem to look kind of nice. But also just that this is a fairly well done hexahedral mesh. And there's not a lot of degrees of freedom that are required for this mesh because it's able to be a linear hexahedral mesh as opposed to a degree 2 quadrilateral mesh. We'll also talk a little bit about like meshing of assemblies. And so this is an example of a piston that's been meshed. So multiple different parts of this assembly have all been meshed to match up to each other. And again, we just see that in this example of with two parts that are merged together, again, there's just like this almost psychedelic, beautiful looking pattern that tends to go on. And again, like we're flowing with these external surfaces. And the same story goes here. Another kind of beautiful hexahedral mesh. And then just to contrast it with here, we see a high degree tetrahedral mesh. The nice thing with tetrahedral meshes is that they can be fairly easily adaptively refined in certain regions. Here we can see though that it may be difficult to note, but if we zoom in, we might be able to see that some of these edges on these triangular faces of the tets appear to be curved, and so they're a higher degree tetrahedral mesh. But there are cases where these elements are desired. And again, another complex geometry assembly. In this case, we have a mixture of tetrahedral elements and hexahedral elements. So we might be, say, choosing to have hexahedral elements in a case that we absolutely really care about, and maybe tetrahedral elements in an area that was maybe difficult to mesh and maybe not as important to the solution that we care about. So with that, I also want to mention that I'm going to provide a couple of papers that I would recommend that you read through. First of these papers is comparing tetrahedral and hexahedral elements in finite elements. Really, I think it's a good read to go through, but they also talk about spline elements. And so in our class, we're talking about smooth basis functions with splines. And kind of at the end, as you read through, they have the authors summarize some of the results in this diagram where they're defining the different kinds of elements, and then green, the arrows point from the better solution to the inferior solution, where then these yellow boxes mean that they're essentially comparable. So this is part of the conclusion of this paper, but I recommend that you read through the paper to try to understand what they've done. The next paper was presented at conference, but is from Sandia, and they talk about in this paper some various different hexahedral mesh algorithms that are used in their qubit meshing software at Sandia. And so they just talk about some of like some important concepts in constructing hex meshes and working with CAD to create hex meshes. And so I recommend that you read through this paper as well, at least at a high level. And lastly is a presentation from Jeff Erickson at Illinois, talking about some of the theoretical advances in hex mesh generation. And this is a really good survey, I think, in constructing meshes, where whether you're interested in maybe more of a biomechanical applications or fluids applications or kind of this more mechanical part that they've got. He's got a lot of good discussion on a lot of the kind of the state of the art, but also some of like the basics of hexes. But specifically, if you read nothing else, you should read the summary and read his takeaways here, as well as kind of the open problem with hex mesh generation. And then I absolutely agree with the sentiment here from David Baraf that maybe I don't hate meshes, but I hate generating meshes. And it is very difficult to construct good hexahedral meshes. So I agree with this sentiment very strongly. All right, so with that, we're gonna go ahead. I'm gonna provide an assembly or a CAE model or file that's going to contain some geometries for you to construct some hash meshes on and to walk through with me in class. So the very first geometry, so there's several models in here, and so you can work through several of these different models, but I'm going to focus in this first part on the simple parts. And there are multiple parts in here. I probably won't provide the meshed, although maybe I'll provide the mesh geometry so that you can have a reference to, because this is really more meant to be a guide for you. So what we need to do in this case is, you might be able to visualize what a hex mesh might look in this or on this part. Unfortunately, Abacus can't visualize like you can. It needs to be able to be provided of some simplified geometry regions that it knows how to construct a mesh on, that its algorithms are designed for. And so mesh generation is really all a game about taking the geometry and kind of constructing a very coarse hex mesh on the geometry side that then Abacus knows how to say refine. It's really kind of what this really is. So what we want to do is we want to decompose this geometry into kind of simple regions. And so maybe the first thing that we see is that we kind of have two dissimilar shapes here. We have a circle, and then we have a cylinder, and then we have like a block. So maybe as the first step, what we're going to do is we're just going to split the block and the cylinder up. What I should say first is we should switch over to the meshing module in Abacus. And again, we'll note that the default color is orange, for Abacus doesn't know how to mesh this. And so if we were to try to click mesh, it'll give us an error. Now, we could just throw in the towel and say, give me tets, and mesh this geometry with tetrahedral elements. And we see we have 1,800 elements. If we query the amount of nodes for our mesh, we have about 3,300 nodes. And so remember, our stiffness matrix is going to be a function of the amount of nodes that we have in the problem. I'm also not very comfortable with having a single layer of tetrahedral elements where essentially we've connected one surface to the other surface. So I'd really probably want to have this geometry at least refined to the level that we are down here with 2 elements through the thickness. And so if we were to say query this thickness on this geometry, so it's so the thickness is 2. So if we take our seed size and we say 1, this should give us 2 elements through the thickness on this top. Now obviously we've got maybe more elements down here that we need, but we can just see that we've got maybe now 20,000 elements. If we query the mesh, we have about 31,000 nodes. And just compare now, if we were to say instead that this could say be a linear a linear tet mesh. So now we see now the curvature's gone away. That this goes down to 4,000 nodes. So just notice that swapping between a linear tet mesh to a quad tet mesh is almost a factor of 10 from the degrees of freedom that we've had to add to our system. So, anyways, I mentioned we're not going to do this with tets. We're going to do this problem we're going to show how to mesh with hexes, but I just want that to be at least a reference for us. Okay, so as I mentioned, let's go ahead and let's separate the cylinder from the block. And we see right now everything switched to yellow. That tells us the abacus sees two different sections or cells, and we can plot each. We can see each cell by itself if we choose replace and replace cells, and so we can see each individual kind of building block of this mesh. So we see like this is how it's going to mesh this bottom block. Remember, it's going to have to try to conform to these edges that when we sliced that cylinder off, the cylinder remains kind of like its image has been imprinted onto our block. And so abacus will try to mesh while respecting that. And so if we click mesh, we can see that abacus has conformed the meshes to the surfaces of the cylinder. We have 3,500 elements, again compared to even in our very coarse TEP mesh was 1,800 elements. But here we have 3,500 elements, and we don't have any single elements through the thickness. If we query the amount of nodes that we have, we're sitting at about 4,000 nodes. Again, compared to essentially the same degrees of freedom as our linear TEP mesh was for the seed size. But again, remember for that seed size, for the TETs, we had to go with quadratic. So we were up at 31,000 nodes. So earlier I mentioned that typically if you can construct a hexahedral mesh, your problem sizes tend to be smaller. And we see that here. But I'd further argue that this isn't a very good hex mesh. So we can just, if you look at this aesthetically, it kind of looks kind of dirty. Let's do a parallel projection here. Kind of see like our mesh on this top surface doesn't really seem to be consistent. So maybe we want to do some like further meshing, preparation. So they call this process of breaking this single part into multiple parts, they call it decomposition. So we're going to do some more decomposition here. So first, one of the things I'm going to do is I'm going to I want to take this this cell here, and just if you notice, if we turn off our displaying our mesh, on one surface we have several surfaces involved. We can just highlight them here. We have this surface, and this surface. While on the bottom we have only a single surface. So this is also kind of a bit of an idea that, well, maybe I can give a bit more structure by projecting this geometry through. So I'm going to go ahead and partition this cell by cutting it. So I'm going to use the partition by face or extend face and use this cylindrical face here to partition it. We now see that that has been propagated through this blocky geometry. Also going to then partition this geometry with the inner surface. Oops. With the same method. And now we see in the bottom, I've now got this projected all the way through. And so what I've really done here is I've now, if we strip away these cells, I've taken this geometry, or this bottom cell, and I've split it into 3 smaller sections. And abacus, again, is able to, again, construct our hex mesh on this geometry. But again, we're still, doesn't really look very pretty yet. So the way you can think about this is that abacus, it can figure out how to put hexes along this cylinder, but it, if we look at this cylinder by itself, it doesn't really look like a hex. Sure, you can see how you can like stretch and warp hexes to fit it, but there's not really a topology of a hex. So what we're going to do is let's go ahead and let's partition this cell with a plane normal to this edge at this point. So this arrow here is defining essentially the normal of this plane cutting through here. Now abacus is cutting back and showing us everything, and now we see that the green is actually shown, or this cylinder is now shown as green. And you can see how now we have a cell, if we look at this cell by itself, that you can kind of see like here's a quad. Here's one face of a quad. Let me just see if I can select by itself. So here's one face of a quad, another face of a quad, a third face of a quad, and a fourth face of a quad. So it's like there's your quad. You've like shown to abacus how to put a quad on this surface, and thus a hexahedral throughout this geometry. So like this has the same topology as a hexahedral element. And so now we can have a structured mesh there. So if we show the mesh again, now look at how like beautiful like this mesh on the cylinder looks. It complies as like this geometry is rotating through. It's symmetric. Like that just looks really pretty. But now our mesh still on the bottom doesn't look very pretty. And part of that reason is that we didn't propagate our decomposition through the geometry. So let's go ahead and do that. Let's go ahead and let's select these bottom 3 cells. And let's partition it with a point and a normal direction. Okay, so that doesn't seem to have changed very much. If we say mesh this geometry, right, maybe it looks a little bit prettier. I mean, it actually looks a lot more beautiful along like this face or this surface here. But again, it looks kind of ugly along here. So, well, it seemed to make sense that earlier when we partitioned along here, we got good hexahedral matching here. So let's go ahead and let's decompose everything by maybe the other direction. Wow, and now our entire geometry has turned green. And so if we construct a hex mesh here and show it, now we have this mesh that looks pretty kind of beautiful almost, right? We're like following all of our hexahedral elements along like this base where there might be some stresses are following the overall shape of that cylinder. So yeah, this is a really good mesh. Again, we see 3,200 elements, and compared to our original mesh was at 3,500 elements. So we've even been able to decrease our element count a little bit. One of the things you can do is you can go ahead and you can compare your TET or your mesh quality or evaluate it with this verify mesh tool. And so let's go ahead and it'll give us some metrics, report some metrics. We'll see some elements might turn yellow or purple if they're good or bad. If we do this, it says none of your elements even constitute needing a warning that they might be poor shape. So those are 3,200 almost perfect elements. And if we go back a couple steps, maybe, so let's maybe come into our geometry. We've seen that all of our partitions that are showing up here as features. We can maybe suppress all but our very first partition. And if we meshed this first hex mesh and verified the mesh quality, right? Again, we see that there's no bad hexes. So even this mesh, even though it doesn't aesthetically look as good, it's still a pretty good mesh. If we go back all the way, again, these are quadratics. We plot the mesh quality. We'll see that it also is of high quality. And so this is a very simple mesh, but I want you to practice as we construct meshes on different geometries to go through and run these checks and see whether or not you have a good mesh or not. And also to maybe try to see like where the porous elements are. So for instance, I can make this mesh look pretty bad by taking some regions and say distorting the size a little bit here, so maybe like down to 0.25. And if we do this, I think we'll get some bad elements. So let's go ahead and, oh no, we're all still good. All right, well this just geometry is pretty simple, so it's gonna be hard for us to get a bad mesh on it. All right, let's move to this geometry. So it's only a slightly different than this, if I just put back these partitions. But now there's like a little slot that's cut through here. So let's go ahead and let's evaluate. Let's maybe take our same process that we did previously of let's go ahead and partition by some faces here. So let's just go through and chop some of these up. Oops, we need this inner cell here. Okay, and if we mesh this, right, we can start to see maybe like in the middle here, there's not really like this great mesh here. Let's go ahead and do our partitioning on the on these edges. So this mid plane here, cut this guy. Actually, what I wanted to do is actually even back. Let's actually go back a bit. Oops, that's not where I wanted to be. I wanted to be in this guy. So what I want to show is actually this. If we partition this geometry kind of simply, let's maybe put a little bit of a refined mesh here. Right, we can kind of see there's maybe like, you know, the mesh kind of varies in this region, as well as like the maybe a poor mesh out here. Anyways, as we go through our geometry and partition, all right, and then maybe do a new mesh. Right, we can kind of see that there's still like we haven't really been able to communicate across that. Here's these two surfaces that have nodes that kind of line up, but you see how like this element here tracks from like this element out on the outer surface to the inner node on this surface there. So essentially, abacus doesn't know that it can communicate this information across, and so this is kind of like the art of trying to decide how to like communicate information across cells to get yourself a beautiful mesh. And so in this case, it's actually fairly simple. We can do that partitioning that we talked about earlier of extruding this cylindrical face. So this will extrude the face up and down, but also radially. Right. So now you see how like there's this geometry edge that now is connecting these two surfaces, and so our elements are going to conform with that general shape. And so if we mesh at this point here, we'll see that they do in fact kind of walk all the way across. But still, this node on the inside kind of like walks into the middle here, and you know there's just not as like clear path for it. So this is why we're going to go ahead and do another partition of the whole geometry with the interfaces. Okay, and so we could stop here, and this is probably a fine place to stop. So you can kind of see how we already have our kind of beautiful looking geometry. It looks fairly symmetric. It looks like it conforms to the geometry. Another decomposition we could do is we could say, well, I want maybe this face here to communicate all the way out. And so we could say take our geometry, this face, as well as with. Right, so now we've seen we've got like these kind of like slot-like regions, and we can mesh those. And it hasn't really changed our mesh very much. What it has done is you can kind of see that if we flip back and forth, there's these element edges here that now we've essentially said, I need an element that, as opposed to being like pointing like almost like a ray into the element, like you might see on some of these elements here where they kind of are pointing inwards. They're now forced to kind of be skewed a little bit. I mean, they're still good elements, they're still fine, but this is a case where maybe it's like one step too far, maybe one bridge too far. So let's go look at an I-beam. So this, for you civil engineers in this class, this should be a nice problem to look at. And this I-beam has some fillets on it. And there are various different. If you read through the PowerPoint from Jeff Erickson I talked about, there's some different meshing algorithms, and you can change the hex meshing algorithm that Abacus will use by searching the mesh controls. And you can see it's got an advancing front algorithm. It also has a medial axis algorithm. And we can say like try out this medial axis meshing algorithm. You can again kind of see like the coarse mesh it's going to be creating. I think this would be useful for you to compare to the presentation where he talks about medial axis meshing. Maybe let's go ahead and like give ourselves a bit of a finer mesh here. And anyway, so this is a fairly like pretty good looking mesh. It's pretty well oriented. Something that's a good rule of thumb is that whenever you have like fillets or cylindrical surfaces, you want to try to have elements that align, like at least that first layer where elements align to them. You don't really want to have a lot of non-structure in those areas. So this is a case where medial axis works fairly well. There's a lot of cases where medial axis, at least in Abacus, doesn't seem to be as effective at. But we can go ahead and switch back to like advancing front. And again, we'll see that the advancing front method, this is one of the things I was wanting to kind of I think we see some issues up here, yeah. So this is the case where, do you see how on this surface now I've got this element that's involved because it's got a single node on this point, but it's nowhere near to being oriented along it. And then, so we actually see there's actually 4 elements that are involved with this fillet. 2 only at a single node, but we really want to have like these faces that are aligned with it. And so this would be a case where, this is just like one of the idiosyncrasies of meshing, that on this fillet it's undesirable, but this fillet over here is exactly kind of what we're looking for. Hexes that are aligned with that fillet. But let's go through and let's do some decomposition on this geometry. So I'm going to delete this mesh, click and hold, and drag over to delete the mesh. So first thing I'm going to do is there's obviously some symmetry here. So let's go ahead and like cut our geometry by like the big symmetries that we see. I wish I could turn these off. At least these to be large again. Here we go. Okay. And there's another symmetry like down the middle. So let's go ahead and partition both of these cells. Point and normal. Okay. And again, one of the things I like to do is I always like to kind of like update my mesh as I go and kind of see like the current state of my mesh and what it might look like. So this is a really kind of, especially as you're learning how to mesh, this is a useful tool for you to be able to do. Okay, so still not quite where I want to be. So something you'll come to realize is that oftentimes when you have fillets, hopefully and usually fillets are aligned, and so there's 2 ways you can partition this fillet. You could either choose to have the normal be kind of to slice, like continue this like line up, so that would be this normal direction. But if you see this, there's going to be like this like entrant kind of like wedge almost. If we mesh these, you'll get like these really highly skewed elements. And right, if this thing is tangent, as we increase our mesh density, say 0.1, like these elements just continue to just it's going to take a little bit. So you can just kind of see like these hex elements just continue to like come flying in here and get really small and really bad quality. And if we were to look at mesh quality here, it's telling us that, hey, you've got some pretty bad elements. They're not necessarily inverted, but these elements are pretty poor quality. And with any amount of deformation almost, these elements could very easily invert on us. So let's go ahead and delete that mesh. Let's also delete this partition. That's the wrong partition. It's in I-beam. So instead what you'll find is that the preferable way to partition these fillets is to partition kind of orthogonal to it. So to partition this way. So now you can just see that this is like a right angle here. So we're constructing right angles. And really when you partition, you want to try to make partitions such that you retain as right angle as possible cuts. And so we'll just follow that same kind of rule of thumb on this top geometry. I guess I'll only do one of these at a time, but we can do the top. Well, let's do these bottom ones first with this same partition. And now let's go ahead and do these. So you probably saw this, but the default highlight is this blue point normal. So I'm using my middle mouse button to just accept the default setting. And so I don't have to click and move my mouse and click. Okay, so here's our resulting hex mesh. Sorry, not our hex mesh, but our decomposition. Oops, we want to change our mesh seed size here back to something that's reasonable. Say size of 1. Okay, and so what we can see here is, again, we've got our hex elements are aligning to our surfaces. So, but what I also want you to see is that if you kind of look at this decomposition, everything here kind of looks a bit like a hex, right? So certainly like this green block here is a hex, right? The only things that aren't hexes are these kind of internal kind of sections. But you can kind of imagine that, and this is what we see with abacus, is that their meshing algorithm is able to essentially auto-decompose this kind of section into kind of an almost hex and then like another almost hex. And then it throws this little extraordinary point in the middle to kind of like link the two things together. So anyway, that's how it's doing that. Sometimes what you'll want to have, say, a certain fillet. So say this is a fatigue analysis or a stress analysis sort of problem, and you really cared about, say, like the stress along like the surface to like a certain depth maybe. So then one of the things you might do is you might come in and you might say, maybe partition some faces. Maybe even just specifically a single face. Let's just do a single face for now. And you might say partition this face with some circle. You might define just from a let's show this that let's go ahead and make an equal distance constraint between these 2 points and this geometry point on our circle. And then let's go ahead and define a radius here. Maybe not even a radius, but we can put another point on this curve here. It's already coincident with this cylinder. We can also make it coincident with this edge here. And we could put, say, a thickness dimension here. And so maybe you wanted it to be like a 1/4 inch. So now you partition this face, and we could then extrude or sweep this edge. So we select our face, we select the edge, sweep it along this direction. And now if we do this mesh, right, we see we have finer elements there, but we could even further say that, well, I want, say, 4 elements through this thickness specifically. And so we can say by number, give me 4 elements. And again, this is a structure mesh, and now in like the far distance is going to go ahead and it's going to like increase the size of these elements outwards. If you didn't want those two, obviously we could have partitioned this entire face the entire way along and put those elements through. Because obviously some of these elements may not be of high mesh quality. But this is also where if we remove this constraint of having to be structured on one of these sections, to say only being swept, it's now able to handle this idea of this coming through. So, anyways, there are some various different things you can play around with constructing these meshes. Lastly, there's a problem with these blades, and so I just want to like walk through. This is maybe a bit of a challenging problem to think about, how to construct a mesh. But one of the things I typically try to recommend is that you try to like just first make some very simple cuts of your problem that make it kind of blocky. And so maybe think for a little bit, maybe pause the video and think about where you try to first kind of like separate out the problem a little bit. Okay, so if you've thought about that for a little bit, we'll come and I'll show you the approach that I'm going to take. So my approach is I'm going to try to split these into 3 or actually 4 sections, maybe 5 sections. I'm just going to split up. I see like these fillets, and I'm just going to take these fillets and just start doing some cuts and start blocking this into blocky regions. And I'm going to essentially, by partitioning in this manner, I'm going to decouple each of these like blades from another blade, so I can focus on each one individually. And we'll see that as we go through, we're already constructing some regions that are already meshable. Okay, and so now I'm left with these blades. Now notice that, not to get yourself too lost, you're like, you might be thinking, oh, well, I'm just going to like take all these fillets and just do planes. Oh, I'm going to take this fillet here, I'm going to cut it with this plane. Right? Well, because again, this isn't planar, right? We have like an edge here, but it's definitely not planar. And so we can even start to see maybe some hints that there's a significant amount of things that are not necessarily orthogonal to each other. So that's clearly a bad partition. So let's go ahead and remove that partition. Something else that we can see is that I've got like these holes and like plate in a hole, kind of what this looks like. So we might be coming back to that. What I like to do oftentimes is to give myself some view along a kind of a uniform direction. And to just note how if you have a perspective view, it's sometimes hard to see if things are concentric to each other. So oftentimes I like to work with perspective off, also called parallel. And then we can swap into, say, transparency. And so we can see that, okay, cool, all of these circles are concentric. But also I'm kind of a bit curious about all of those fillets that we saw. So I'm going to go ahead and remove all these sections I can already mesh. And I just, undo. I just want to see, could I possibly do something with like these fillets? And maybe it's a bit hard to see still. I might choose to see, okay, I do have extra fine, but these fillets do line up with each other. So importantly, on a single blade, I could say sweep this fillet edge through to this fillet edge. So they're one-to-one mappings. So I'm going to go ahead and do that. I'm going to go ahead and choose this cell to partition, select this edge, and then I'm going to sweep it along this edge, along this direction. Okay, and so now you see how we've got this single cell by itself and this single cell by itself. And this again looks similar to like what we saw in the I-beam. So I'm going to go ahead and do that for these other two. Oops. I'm going to go ahead and partition U, grab this edge, sweep along this direction, or extrude along this direction. And same for this cell, along this direction. So there, I've got a hex meshable object now. You can just click Hex Mesh. And there we go. But again, we see that, well, this doesn't maybe look the prettiest. I mean, it is a hex mesh, and if we look at quality, I'm sure this, well, so some of these maybe aren't great. Let's go ahead and just take a look. Yeah, okay, we can see I've got, yep, so there's this string of hexes here. Yeah, we can just see like those hexes look pretty gnarly. So here's something I can do is we see maybe there's some asymmetries here, and this maybe kind of screams out that, well, what I could do is I could say partition this geometry with a plane right along, you know, with this normal here. Cut them in half. And if we just compare this mesh now, I'm still aligning with my fillets, whereas here I wasn't really aligned with my fillets. I got this nice kind of like structure. We could also maybe choose that maybe this cell just needs to be a sweep. And maybe that looks a little bit better, except again, we have this hex here that doesn't really flow with our fillet. So maybe not that great. But we can kind of see just from this side view, if we can get a good side view, maybe not, that just the three different mesh types what kind of approaches that we've taken so far. So I guess it's from this orientation. So anyways, we kind of like this one better, so we're going to go ahead and do this partitioning for both of these other two. And then we'll reconstruct this mesh. Again, this mesh is looking pretty good. But you know what? Maybe we still don't like this mesh looking down the top. Well, from our previous study, we know that we can go ahead and do we can partition all of this geometry normal to this edge. Cylindrical edges. So I notice I picked normal to edge. Select this edge, and then a point on the edge. It's kind of hard to see, but there's some yellow vertices. There's a yellow vertex here. This cuts through all of those cells. And we'll construct this mesh. So now at least we've got maybe some, you know, close to symmetry. It's not quite symmetric. We see some variations. But now I'm going to do another partition where I want to cut these. Maybe I want to cut these like kind of like in half. And again, the naive approach might have been to say, well, I'm going to take these top cells. I'm going to pick the circles, and you know, from a normal direction standpoint, like this, let this be the normal. And again, we see, whoa, that's a bit off kilter, off center, right? We don't really have orthogonal cuts here. But even if we'd cut this geometry with well, and you can see if I cut with this being a normal direction, it would actually be kind of slicing through. We'll go ahead and see that here. If we cut this geometry again in the center of our circle with this, say with this normal direction, right, we can see that this kind of cuts downwards through. And so that's maybe not what we want either. So the question is how to handle this. Well, we can kind of see that we could cut a circle or some circular cross section out of this. The question is how to do that. So what we're going to do is we're going to create a datum plane. We're going to offset it from a surface, so from some other plane. So I'm going to select one of these faces here, and maybe I'm just going to pick some arbitrary value of 20. So I have some now plane, and I'm going to say choose to partition a face. I'm going to choose these two faces. I'm going to choose my sketch plane to be this data plane I defined. It turns purple. And I'm going to choose through all. And then I'm going to choose this, maybe this face or this edge here to be vertical on the right. So now I've got this sketch that I can put together. I'm going to go ahead, there's a function for project edges. So I'm going to go ahead and project the edge from this geometry or this cell here. Just that gives me now this like a circle that I can use with like a radius point. And so I can say make some circle. I can also make a construction point from the center through here. And so I'm doing that so that if I can get my plane back. So it should cut through the middle of these circles here. Choose a constraint to put this point on my circle on this construction line. And then now what I can do is I can project this circle up. Now this is maybe outside of this lecture here, but you might have thought, oh, I have a circle, I'm going to project it up, and now it's going to be another circle. But it's not actually. These again, there's a circle in a different plane. It's now being projected up to a plane that's not parallel to itself. And so these end up being transformed into non-uniform rational B-splines. But what I do at least have is I do at least have a point on this curve, or 2 points on this curve, that I can now say, hey, by the way, because these are at the max and mins, equal distance these 2 points to this point on my curve. And now I've essentially bisected, what the circle would be down on that plane. And we're going to need to just turn these two curves into construction lines so they don't get actually used on the surface, but they're allowed to be used in our sketching. Okay, so that's now that face partitioned, and you can see how it's orthogonal to the circle here and also orthogonal to these faces here. So we'll go ahead and now sweep these edges through. And I'm just going to select all those faces. I can only select, I guess, one of these at a time, so we'll just extrude along direction. Again, directions any of these straight edges down here. And we'll do the same for these cells. Sweep along this direction. Oh, I didn't select those cells. So we just need to, let's just go back one stage and do this one more time. 1, 2, 3, 4, 5, 6. Okay. And so now we can go ahead and put this hex mesh on. And now this is looking significantly better. It's not going to be perfect, again, just because we do have this circle has been kind of chopped out. But this is actually, that is actually a really pretty gnarly, pretty horrible mesh or element here that we'll need to resolve. So we'll see this show up in our quality metric here. We should maybe I can't believe that that's a a hex element. That's got to be a wedge of some sort. But that should absolutely be some sort of error. Don't think this is the case, but we'll just give this a look. Yep, so what we can see here is there's this kind of additional, there's really small edge. As we zoom in, you can kind of see, ooh, it's going haywire on me. Yeah, so we actually see multiple different points along this. So again, remember we said that abacus is going to, whatever geometry definitions you have, is going to map to them. So I've got like edges. It's going to try to match these hexes to these edges. So some, and just note, like you can't really even see the fact that there's this super small edge. Right? I have to like zoom in to see this edge. And so this oftentimes crops up as like just things that kind of are annoying. Sometimes you can get away with trying to remove redundant entities and remove as many as possible. Maybe now if we move in, we can see that now a lot of those extra yellow points have gone away. And if we zoom all the way in as far as I can, it looks like these points are now, there's just a single point there. So there's no single small edge on this geometry. And so if we swap back over to the mesh and then remesh now, there we go. Much better mesh. So anyway, so that was so that kind of covered a couple things, mesh generation, but also some of the troubles with dirty geometry or bad geometry. So these are what I would consider simple parts to mesh. I want to show maybe like what happens when you're dealing with like an assembly. So here I've got a geometry with two parts, a bolt and a plate. And if we look at these in as an assembly, well, I've kind of given away a bit of the secret here, but let's maybe do, let's bring the original guys in, and then just make concentricity coaxial. There we go. So this bolt is meant to mate with this plate, and we can see, may not be extremely clear, but let me just switch over to part instances. All right, so this bolt is a perfect fit into this plate. All right, so the geometry is exact, two exact circles that exactly match. But what we'll see is if we switch over to meshing, if we just say take this course or this geometry and we do a mesh on it, and we take the bolt and we can just get ourselves a simple mesh by simply partitioning with this face here and throw a mesh onto this guy. So right now we're meshing the parts by themselves. You can't really see the other geometry. If we switch back over to assembly mode, we'll now see that, let's turn off our view cut here. The geometry doesn't actually now, we've got this like overlap that you might be able to see. You can kind of see if we look down the top that some of these hex elements of the coarse geometry, right? So it's got to be linear, and they're like intersecting like this green geometry. And so there's overlaps, and we can see this maybe a bit clearer if we choose to remove elements. Let's just select a string of them. So again, we can see that here's this overlapping geometry here. And so now we've suddenly taken this problem where they say there was no interference, and now we've assigned an arbitrary interference. And so this is a challenge when we're using. This is part of the thing we're going to talk about in class about isogeometric analysis. That if you're defining your geometry with smooth splines or non-uniform rational B-splines for the case of the circles, but then you're transforming your geometry into linear facets, you're no longer going to be able to have perfect mating between parts anymore in many cases. And you can imagine that if this was a bolt that was kind of rotating through, it would be essentially kind of ratcheting through as it's varying its overlap. So that's a different topic for the class to talk about, is this isogeometric analysis part. But what we can do instead is in abacus, we would go ahead and we would unite these geometries. In other meshing software, they might call like imprinting and merging of surfaces, but in abacus we end up having to actually unite the parts in an assembly mode, which is this Boolean operation, merge cut instances. We'll call this merged part. And then we'll choose to retain the intersecting boundaries. So they'll kind of retain like these cells for these two parts. So that's now a new part in my model called merged part. And I can see that I've got two cells. Actually, I've got multiple cells, I suppose, because I had previously defined this bolt to be two cells. And so now here we could go ahead and we can mesh. So I could choose to say mesh this entire geometry with, say, a cut down this plane. If we switch back over to the mesh module, switch ourselves back to the default plot colors. So now I've got to have a mesh, and this mesh is now at least, we won't worry about getting this all the way through to a pretty mesh per se, but just now at least my mesh is aligned. But I have merged this is now a merged mesh, so I no longer have like a bolt here that can just like stand off by itself. So I wouldn't be able to like rotate this bolt or anything like that. But I just thought I'd just show this just because there are oftentimes are cases where in your geometry you'll just merge some parts together. But preferably is this kind of this concept of imprinting and merging if you're able to do that. I want to also show, say, a bad part. So we talk about like mesh preprocessing and just different various things. That one of the things you'll oftentimes get are parts that A, are difficult to mesh, but then B, maybe just like have a bad part definition. So just if we look at this geometry here, we've got like again this fillet that comes in, it's kind of goes off to tangent here at this point. And we've got some maybe very small fillets. And we might decide that some of these fillets we want to just like get rid of because they don't matter for the simulation. But specifically, what I wanted to bring your attention to, I'm going to do a partition, or a cut here, is, let's see, which one do I want this on? That's pretty fine. I don't think I can do multiple cuts. All right. So here's a case where on this surface I have a fillet defined between this surface and this surface. And so my fillet goes all the way around. But the designers also defined these inset holes that are going to be machined either through drilling and then pushing out or boring in. But just think about it, like, how in the world are you going to manufacture this part? How do we propose that we're going to be able to machine something down to effectively, if it's a fillet, to 0 thickness here? And the answer is that would be very difficult. Like, if this is your part definition, you'd never be able to manufacture this. And even if you did somehow manage to manufacture this is going to be a very weak point here, as well as it's going to be sharp. And so from a hazards and health and OSHA standpoint, this part's going to be effectively impossible to use. And so what I have found is that in mesh generation, you oftentimes are sometimes the front line of finding errors in part definitions, just because of the rigor that it requires to construct a hex mesh for. And so, to be honest, I wouldn't even attempt to mesh this geometry. If I saw this at this point, I'm just sending this back to the designer and telling him, you've got a problem, and you need to fix this. So that's just a bit of a word of advice there that I would give you. Next I want to show is this kind of bracket with fillets, and this is a bit more of a complicated geometry that we're going to walk through. And I'm just going to mostly just walk through, maybe a max decomposition kind of state that I might try to get to. So again, say I care about every single feature in this geometry, so I'm not going to do any defeaturing of any of these fillets or anything. I'm just going to kind of maximally decompose this geometry. So maybe a first step I always like to do is we handle these fillets. So I'm just going to chop here. I'm going to chop this geometry. It's the same way. I need this edge. And then this on this edge. And then you need to be partitioned. Partition this. Okay, and you're fully partitioned. And so then what I'm going to do is I'm going to maybe come through and I'm going to select all of these surfaces or cells and chop them down the middle. And I'm going to do the same with this cell here. Chop down this way. And then let's see. So another thing I can do is I can kind of see that I can chop off this extra little this fillet. So that's going to be maybe an edge sweep. Do that for all of these. So I might first choose to do these edges. Sweep along this Z direction. And then this guy I can just chop with the plane. I want to select multiple at a time, so I'm going to select by edge angle. That's going to give me all those edges though, so I don't want that. I just want these edges. I'm holding Shift to select multiple, and Control and Select would deselect objects. Plane. And I must have missed this guy earlier. So you can see now I've got pretty much all hex meshable except for certain small regions. So if I look at this guy, how do I put a hex on this? Well, maybe what I'll try to do is maybe I'll try to sweep, because I haven't swept yet, this guy through. There we go. Let's do the same for these. Okay, so here's what appears to be a hex meshable object. But if I ask it to hex mesh, even though it says, hey, all these things are hex meshable, it's going to tell me I've got some incompatible interfaces. And just know it's going to say it's going to generate tie constraints across those interfaces. And it's okay to maybe proceed. Does look like we're having a mesh or seed propagation issue, so maybe we won't be able to mesh it. Yep, so still not able to mesh it. So okay, so even though everything here is hex meshable, it's able to propagate. So oftentimes what that is that structured meshes, well, they're structured, and so they have a lot of constraints on them. They constrain like your algorithm a lot. So sometimes it's good to come through and turn things back to sweeps. Sometimes that helps. Other times it doesn't. Let's see. What's something else we can do? Sometimes it's helpful to mesh by section. Okay, so there's my incompatibility. It's able to mesh. Well, this could be a spot that we can kind of see that maybe I want to add a partition here. Add a partition here. Do that for the rest of these. Okay, so here we've kind of like helped guide Abacus through meshing the whole geometry bit by bit, and we do have a hex mesh. But what I want to show is I want to show, like, on the surface everything looks hunky dory, looks all good. But if we view transparency, you can kind of see, you might be able to see this on the video, there's some sections that look kind of like they're not transparent. They're almost like translucent. And so let's go ahead and let's just maybe drive down. Let's maybe turn our transparency back on, and let's just like see if we can dig down to find like where this is coming from. Oops, one too far. So it's clearly these two cells here. And so then if we go ahead and you can kind of see a little bit of like this mesh transition here. I'm going to go ahead and I'm going to remove or replace elements here. I'm going to try to replace just along or hold only the elements on this interface. By edges or elements. And so what you can see is that some of these, just these nodes aren't lining up. And so as opposed to a merged mesh where all of our basis functions have, between elements, the elements are C0, which is what we've been traditionally doing. Now we've got nodes where they're discontinuous. They don't match up. They're not continuous at the element nodes. And so what Abacus, so this is essentially disconnected regions. They're not able to transmit information across their interfaces. So what Abacus will do is you can add in a tie constraint, which effectively puts in some linear relation between the displacement of some certain nodes to others. So there's this algebraic constraint that it applies. And I think we'll cover this in class a little bit, but you really don't want to have tie constraints in your model if you can help it. But if you are going to have them, you want them as far away from an area that you care about as possible. We've already talked about like issues with C0 finite elements and being able to predict and converge to solutions. But now if you have like these maybe C-1 elements with some constraint between them, they just tend to be even worse. And these elements don't transmit, this algebraic constraint doesn't necessarily transmit like stiffness across it. It's like infinitely stiff across it when it constrains these nodes to each other. So just for a variety of reasons, they're just really not preferred. So I would recommend that maybe you try to go through and see if you can mesh this geometry without needing these tie constraints. Well, on the flip side, we could also say that, let's go back. Let's remove, where am I at? So I need to just get to, we're in fillets, part, and bracket. So maybe remove all of these partitions. So say that you're the engineer and what you care about is maybe we got some like bolts that are loading up these parts, and or maybe loading up this part, and maybe we're pulling outwards on all of these, and we care about maybe like the max deflection that we're going to see. Well, and so if you think about that, right? So this is like now like a bending problem. So there's probably some areas that don't really matter from like the bending problem, right? That we maybe don't really care about. Well, one thing I probably don't care about is that if this is bending, right, I would expect my maximum stresses to be along where these fillets are. And I don't really care about like solving the solution on this chamfer. So back in my meshing or part module, I might choose, there is a function to replace faces. You can do it via extending neighboring faces. And I'm going to choose these chamfers on these faces to just remove. And I mentioned that really what's contributing are these fillets on the center line. So I don't want to remove these fillets, right? If I were to remove these fillets, right, and well, maybe I should just do them all. I'll just fully defeature as opposed to trying to be quick with it. If we were to choose all of these fillets to remove, well, now I'm going to have like stress concentrations here, and this maybe isn't going to be an accurate. If I really cared about the, well, I should have probably also removed these fillets as well. But if I really cared about, so here's like this fully defeatured model. If I really cared about this deflection, I really do need to have an accurate solution along this place of bending. I could even have gone like a step further and like removed like these cylinders as well, and then just like, maybe applied some like load. But right, we've already seen a cylinder and a plate isn't necessarily going to be a difficult thing to mesh. So let's maybe go back. And let's think more judiciously about what regions, what fillets to remove. So it's probably clear that, like this fillet on like the top surfaces that are far away from like the bending maybe don't matter so much. So maybe you might choose to so probably needed to choose analytic. Extend. Make sure to have extend neighboring faces on. So now here's a model where we can see that I've really not changed that much, just to like flop back and forth. I've really only removed a little bit of the model geometry that's far away from like the part of bending, and it's not really going to have much of an influence on the bending results. I could also say choose to remove these exterior fillets as well. And so this is maybe now okay for me to be able to predict the overall deflection. But if we now try to mesh this geometry, we can take our same kind of approach of chopping these one by one. Right, so very few amount of cuts here. I've got this hex meshable geometry. And if I mesh it, no tie constraints were needed. And so what you'll often find is that from a design standpoint, people have wanted to make sure they have all the fillets and all of like the fine features and high curvature regions defined in the part definition. But those are oftentimes not important for engineering analysis. And by removing those features that make it difficult to mesh, but retaining the overall accuracy of our simulation, that can usually be a high boom to your productivity. So the assignment that you're going to be given is going to be to mesh one of these three models, or attempt to mesh one of these three models. One is going to be this assembly of multiple components. This might be a case where I recommend not to do a merge unite. And obviously some of these parts here, like this is like an electronic box, so there's like maybe a VGA kind of like cable input, and some of these guys are just hanging out out in the middle of nowhere, and obviously like free floating. So this is kind of a bit of a nonsensical part. But some of these parts are very easy to mesh. But then a few parts that are at least repeated, let me provide you some practice. So like this part, for instance, to try to put a hex mesh on this. So you can choose to mesh this contiguous assembly, which I think is probably going to be the easiest model to mesh. There's also the NIST models that you can choose to mesh. And this is probably the most difficult geometry to mesh, but I do want you to at least come through and on this geometry do a defeaturing run through. So there's a whole bunch of these kind of screw holes that you'll be able to remove with replace faces. And so notice they have like a conical surface. It's not clear, but oftentimes you'll see this in mechanical parts that they'll have these conical faces that you can just, maybe it's not clear, but these are a real pain to try to put hex meshes around. And they're really not that accurate to what's actually going to be made anyways. And so usually a very good first step is, even if you want to have these faces involved or these holes involved, you almost never want the conical face at the bottom to be involved. And so you can remove those fairly, usually fairly simply. I think this is just going to, you may have to do so I guess in this case we're going to delete, we're going to remove this face. It's going to give us a warning about the cell being removed. So now I want to go through and select all those, and then we can cover these edges, fitting an analytic surface, and select those bottom edges. You'll still have a shell, so you'll need to recreate a 3D volume by clicking and holding, and then create a solid from shell. And so you'll probably want to do, this is why you don't want to do this after every single defeature step. So maybe get rid of all of those conical sections and cover them all back up, and then come through with this adding a shell. That'll probably save you some time. And then the other part of this is that you can also remove faces multiple at a time. So instead we could have come through and we could have, say, literally selected all of these faces. I'll only do 4 here. And then we could cover edges for just these 4. So we could shift select through all of these, control to unselect, and then it'll tell us it's going to create 4 distinct loops. So it created 4 faces. So that's how you can kind of like batch process those. Something that's off. Well, yeah, I guess, yeah. So this is it. So anyway, I recommend going through this geometry. Maybe get rid of like this NIST little logo that's been carved in. There's also this bucket. Something else I want to talk about. I'm not going to generate the mesh at all on this, but there is a feature called virtual topology. And so if we go to the meshing module, and if we choose to say mesh this with TETs, so there are some very small fillets that we'll see that maybe it's not necessarily, you might have cases where it may not be clear how to remove a geometry or a feature, but you can instead choose to do virtual topology, which doesn't actually modify the underlying CAD model, but rather just tells the meshing kernel to ignore a feature of the geometry. So we could say merge all of these fillets together, and it's now just has conveniently forgotten that those edges were there, but it'll still project nodes and project elements to the surface. So if we mesh this geometry, you can see how it still, since these are quadratic elements, it still has projected the mid nodes to the fillet. So this is a really good way to be able to capture the overall shape of a geometry without being restricted to the topology of the geometry. And so we could probably extend this even further by, instead we chose in this NIST model, let's undo this virtual topology. Is maybe you want to combine all these fillets in this manner. Right, and certainly like this is something we don't want to have to capture this really small edge here. Anyways, we could propagate this all the way through. And you could even take the more extreme step of then merging them with like the faces. And so if we were to do a tap mesh on this, we'll see that this is one of the challenges with this, is that because the mesh element seed size is so large, it just completely doesn't even recognize that this fillet exists there, and so it's a pretty crude mesh, and it's really a pretty poor representation of the geometry. But if this is in a region of your geometry that you didn't care about, say you cared about the stress on, like, say, like this face way up here, well, you don't really care about this geometry over here. You just want some mesh that's not going to break your simulation model. That would be a case where versatile topology is really useful. Okay, so that concludes this lecture. I encourage you to follow all the steps on the previous examples that I've provided, and then select which these geometries that they are hex meshable. However, the two NIST models are more difficult than the contiguous assembly, and the bucket is probably the simpler of the two. So this model here is probably the simpler of the two NIST models to mesh. But I want you to try using a tap mesh generation tool and do some comparison on element quality and number of elements and number of degrees of freedom for quadratic tets, and compare them to your linear hex mesh that you're able to generate, and provide some feedback and some comments on that. All right, that's it.